Good morning, everyone. So, in the last class, recall that we have discussed Bessel equations and solutions of Bessel equation, which are known as the Bessel function of first kind and Bessel function of the second kind. It means the general solution of the Bessel equation is C1jpx plus C2j minus px when p is not an integer. So today we are going to see some interesting relations or some interesting properties of the Bessel functions. The first one says that x jp dash is equal to p jp minus x jp plus 1. Since we only know the definition of Bessel function, so we are going to use the definition, and we know that jpx is summation minus 1 raised to the power n by n factorial p plus n factorial x by 2 raised to the power 2n plus p, and I need jp dash, so I differentiate with respect to x, and this is how it looks like. Now how do we proceed further? Okay, now quick observation is right hand side I need p jp and x jp plus 1, so I need two terms, and one of the term p is multiplied with jp. So here also when I differentiate I got 2n plus p. So if I break it, it means I will consider this summation, one term with 2n and one term with p, and see what happens. So I write it as summation 2n minus 1 raised to the power n factorial p plus n factorial x by 2 2n plus p minus 1, and you can observe that it was 1 by 2 but I multiplied it by x. So because of this, let's write it so that I can see the change. So x jp dash. Now the next observation is what I need on this side. I need x jp plus 1. So I need x also. So I am not merging this x with x by 2. Yes. Now this 2 and this 2 would cancel out, and this becomes n minus 1 factorial. When it becomes n minus 1 factorial, it means that the summation must starts from 1 to infinity. Yes. And the second term would be p is not part of the summation, so I can take this p, it remains as it is, and now I have x by 2 raised to the power 2n plus p minus 1 and x by 2. So I can multiply this x by 2, this becomes x raised to power 2n plus p, and this p is also important, so I can take it out. Now the first term I need as pjp, as minus x jp plus 1. So I need it in the form of Bessel function. So that's why I want the summation from 0, it is from 1, and therefore I replace n. So replace n by m plus 1, or you can say replace n by n plus 1, doesn't matter. So the first term would become x, then minus 1 raised to the power m plus 1, m plus 1, then m factorial p plus m plus 1 factorial, and so on. And the last term would be p, and rest it can be easily observed become jp. Now in the first term also, if you see in the denominator I have m factorial, then p plus 1 plus m, and numerator would be also, this is 2m plus it becomes p plus 1. So it is in the form of jp plus 1. The only problem is I need minus 1 raised to the power m. So 1 minus I take outside, so it becomes minus 1 minus x, and it becomes jp plus 1. So therefore my required answer is x jp dash is p jp minus x jp plus 1. The next property is x jp dash is minus p jp plus x jp minus 1. Now please do try to solve it by yourself, it's not difficult. Of course I need jp dash, Now if you see on the right hand side I need minus p, and in the bracket I have 2n plus p, but I need minus p. Yes, so what I do is that I can write 2n plus p as 2n plus 2p n minus p, and then I can consider one term with 2n plus p and the other term with minus p. So if you do it, then this is how the first term looks like. Now this first term is 2n plus p, and if I cancel this 2 and this 2 and n plus p with this one, it is n plus p minus 1 factorial. Yes, and actually I need the answer in terms of x jp minus 1, so this p minus 1 is perfect for me. And the next term is minus p, and the rest would remain as it is. If I multiply by x, then from the first term it clearly turns out to be jp minus 1, so x jp minus 1, and the next term easily transform into jp. So that's why this is my required answer. So I got two properties of the Bessel functions. Let's move to the third property. We need to remember all of them. The third one says that 2jp dash is equal to jp minus 1 minus jp plus 1. Yes, how do you solve this? If you go by definition, it can be proved, but there is no point because it is simply the addition of property 1 and property 2. It means if you remember 1 and 2, you can easily derive 3, but it's good to remember the third one also. Fourth one is 2p jp is x jp plus 1 plus jp minus 1. This x is like this. So again, if you subtract 2 from 1, property 2 from property 1, you can easily observe 2p jp is x jp plus 1 plus jp minus 1. The fifth one is d by dx of x raised to the power minus p jp is equal to minus x raised to the power minus p jp plus 1. So to solve this one, let's try to see what is left hand side. So we differentiate. So this becomes jp dash minus p x raised to the power minus p minus 1 jp. Now I already have the value of jp dash, and before that if I simplify it in this form, or I can directly substitute the value of jp dash, nothing, both are correct. So if I take x raised to the power minus p minus 1 common, then it becomes x jp dash minus p jp. Now from property 1, it is actually minus x jp plus 1. This is minus x jp plus 1. So this becomes minus x raised to the power minus p jp plus 1. Similarly, there is one more property, d by dx of x raised to the power p jp. Try it by yourself and it can be easily solved. So you take x raised to the power p minus 1 common and use property 2, which is x jp minus 1. So multiplied by x jp minus 1, that gives you the required answer. Now one more interesting property says that j half x is root 2 by pi x sin x. Yes, again we'll go by definition. So we know this is how we can write down jp. Now in this jp, this summation is over n, and I know the series expansion of sin x, x minus x cube by 3 and so on, 3 factorial and so on. So that's why I can try to take the term p outside of the summation. X by 2 raised to the power p can be easily taken out, and if you see the summation, then this is how the remaining terms look like. Now here if I, for example, substitute p is equal to half, then it becomes The first term is 1 by 3 by 2 factorial x square by 2 square. Instead of 3 by 2 factorial, if I simply have 3 by 2, then it becomes x square by 3 factorial, and if I multiply by x, it becomes x cube by 3 factorial. And similarly, the same observation can be seen from the next term. It means if I take p factorial outside, then this is how it looks like. So this term would be 1 by p plus 1 x square by p square, then 1 plus 2 factorial p plus 1 p plus 2, and so on. And now let's substitute p is equal to half. If you substitute p is equal to half, it is 1 by half factorial. Do you know what is half factorial? One thing, this factorial, to compute this factorial, we need gamma function. It is gamma 3 by 2. Gamma 3 by 2 is 1 by 2 gamma half, and gamma half, if you recall, it is root pi. Yes. So since gamma half is root pi, we are not discussing how to obtain it. It has been discussed in other courses also, and you can easily find it also. So if I substitute all these values, then j half x easily gets simplified in this form. Now in the bracket, I need x minus x cube and then x raised to the power 5 and so on. That's why I can multiply and divide this by root x and root x, and if I simplify it, then it easily get transformed into the required answer. Similarly, if I put j is equal to, or p is equal to minus half, then j minus half can easily be computed as root 2 by pi x cos x. Now let's try to compute j 3 by 2x. Now I already have j half and j minus half, so I should not go to the definition and try to use the identities which we have discussed. Now for the identities, I have to choose the identity where I just need to use j half and j minus half. Yes, so go through all the identities and see which one is the most suitable. So if you use 2p jp is x jp plus 1 plus jp minus 1 and substitute p is equal to half, then it becomes very easy. On the right hand side, you have j 3 by 2. You can take j minus half on the left hand side, simplify it, and get the value of j 3 by 2. So let's move to the last question, which says that find a such that xj11 minus xj10 minus xj10 double dash plus aj10 is equal to 0. There can be many ways. Of course, I have to use the different identities, but only observation is I have j10 double dash, and I know that j10 is the solution of the Bessel equation when p is equal to 10, and there you have y double dash. So if I try to use the Bessel equation, so recall what is Bessel equation: x square y double dash plus xy dash plus x square minus p square y is equal to 0. If I put y is equal to j10, then x square j10 double dash plus x j10 dash plus x square minus 10 square minus 10 square j10 is equal to 0. Yes, so if I simplify it, then x square j10 double dash is in the question, and x square j10 is also in the question, which is 100 j10 minus x j10ish. Now if I see this equation, which is the given equation, and if I simplify this one, then I have x square j10 double dash plus j10 is equal to a j10 plus x j11. So if you see equation 1 and 2 and see the right hand sides, then aj10 100j10 is there, but here I have xj11, here I have minus xj10 dash. It means that I want to write j11 in terms of j10 dash. Yes, so I have to again use the suitable identity. So recall that I have jn dash or jp dash is n by x jn minus jn plus 1, but I need x j10 dash or minus, so therefore I can take minus x j10 dash is minus 10 j10 plus x j11. Now if I substitute the values into equation 2 and simplify, then it becomes 90 j10 plus x j11. Yes, and now if I compare it with equation 1, then your A is 90, which is the required answer. Thank you.